Hello students, this is Professor Chalai, and in this video I'm just going to go over a few of the things that you may need to know for the thermochemistry lab this week. Let's get started. So in your pre-lab, we asked you to write a balanced chemical equation for the dissolution of a solid salt. So you might picture salt crystals as composing of a cation and an anion. As an example, let's use magnesium sulfate. Right, where magnesium has a 2+ charge and sulfate, let's write it this way in this color, with a 2- charge. And they're held together by what we call electrostatic forces. The positive charge and the negative charge sort of all attract each other. Okay, when you add this into water, they dissolve. And what happens when they dissolve is basically water molecules come in. Right, imagine these are my water molecules, and they sort of break and disrupt these bonds and fit themselves all over these molecules. And that's what happens. So we go from a solid magnesium sulfate that has a bond between them to being completely separated as individual ions floating in our solution. Now, just to make this picture complete, this positive charge could have also attracted a negative charge over here, and this sulfate could have attracted another positive charge over here, and this would repeat infinitely in a crystal. But in solution, water comes in between all of these ions and separate them, and so they dissolve. So if we're thinking of writing the balanced chemical equation for the dissolution, we would have started with the solid magnesium sulfate, and as they dissolve, they break apart into the ions. SO4 2 minus aqueous. I used a different example than what your pre-lab is asking for, so make sure you write the correct balanced equation. Okay, another thing that I wanted to go over was just to do a sample calculation for number 5. So there's some resources linked on a site on how to do these. So instead of using the values that we have here, I'm just going to make up some values. So instead of 5.55, I'll use 5.23 grams of magnesium sulfate. I'll use 59.71 grams of water, and our temperature change will go from 23.2 degrees Celsius to, let's say, I don't know, 29.7 degrees Celsius. So let's calculate the heat transferred to the solution. So we know that heat is equal to the mass times the specific heat capacity times the temperature change. So let's figure out each of these in turn. The mass of the solution will be the mass of the solute plus the mass of the solvent, right? Solution is solute plus solvent. So that'll be 5.23 grams plus 59.71 grams. That will give us a mass of, if I can do this math correctly, 64.94 grams. So that's the mass of our solution that we're working with. Now, they give us a specific heat capacity of water. We don't have to worry about that. That will be the specific heat capacity of the solution. So let's look at the temperature change. The temperature change will always be the final temperature, which in this case is 29.7 degrees Celsius, minus the initial temperature, 23.2 degrees Celsius. So that gives us a temperature change of 6.5 degrees Celsius to 1 decimal place. So the heat then of the solution would be the mass, 64.94 grams. 64.94 grams. The specific heat capacity of water, they tell us, is 4.184 joules per gram per degree Celsius, such that grams cancel out, and the temperature change was 6.5 degrees Celsius, so that degrees Celsius cancel out. And so our answer, if we plug these into our calculator to 2 sig figs, would be 1800 joules. So this is the heat from the solution. If we want to calculate the heat from the system, which is the reaction, right? So the heat, and my pen is going crazy. Oh, there we go. My computer's starting to freeze up. The heat from the reaction is going to be negative the heat from the solution, so this is going to be negative 1800 joules. All right, so that's just some of the calculations that I wanted to go over. We all know how to calculate moles of something from the mass. And yep, and then to calculate the energy dissolution per mole, you take the energy here, the heat from the reaction, and you divide it by a number of moles of solute. All right, so those are the things that I want to point out in the pre-lab calculation. In case you haven't seen this, there are links on the A side on how to do these calculations. And if you were in Chem 150, then you would have also done some of these in class already. Okay, so this lab we're looking at, as the lab says, thermochemistry. And so what we're going to do is we're going to do a few different thermochemical experiments. The first part, the qualitative part of this experiment, we're just going to look at whether certain dissolutions, which we went over in the pre-lab, which is basically just breaking apart of ions as they dissolve in water, whether those are going to be exothermic or endothermic reactions. And these are the various salts that we're going to dissolve to look at whether they're exothermic or endothermic. The second part is quantitative, right? So in the second part of the lab, not only do we care whether they're exothermic or endothermic, but we want to know the exact enthalpy change in those reactions. So we're looking for the delta H for these reactions that we talked about. So we're going to set up what we call a coffee cup calorimeter, which is basically a styrofoam cup filled with water. We'll know exactly how much mass of water we have. We'll measure that carefully. And we're going to have a temperature probe in there. And that's not a straight line because my computer is freezing up, but that's okay. It's a temperature probe, which will connect to our computer to give us the temperature readout. And then you'll have a separate sort of stirring rod to stir the solution. So stirring rod to stir the solution. And then we're going to add our solid salt in here to dissolve as we stir. And then we're going to check how the temperature changes on our computer. So if you imagine this is our computer readout, our temperature will be on our y-axis in degrees Celsius, and on the x-axis will just be time. So before you add the salt, right, you'll take a few measurements. Let's use purple. You'll take a few measurements to make sure that the measurement of the water is stabilized. As you add the salt, you'll see either the temperature will increase or decrease, right? Depending on whether it's exothermic or endothermic. In this example, let's assume it increases. So as you dissolve the salt, the temperature will start to increase at some point, and then it'll slow down, and eventually it'll stop increasing. And it'll look something like that. And then you can stop the experiment at that point. So here, this beginning part, here, that's your initial temperature. So you take a baseline there, that's your initial temperature. After it stops increasing, you'll take a line there somewhere. The average up there will be your final temperature. And so if you want the temperature difference, it will be this difference here. This is your delta T for your reaction. So make sure that you wait until it becomes entirely flat before you stop the reaction and take the final temperature. So this is basically our setup for this lab. We're going to dissolve something. We're going to take the temperature increase. We know the mass of the water. We know the mass of the solute, so we know the mass of the solution. We know the specific heat capacity of water. And from this, we can calculate the temperature change. So we can calculate the heat from the solution. We know that the heat from the reaction is going to be negative the heat from the solution. And then we can calculate the number of moles of solute, and that way we can calculate the delta H for that reaction. Okay, so this is just basically the setup of what we're going to do. And in your recording, make sure you record the initial temperature, the final temperature, and therefore you can calculate the temperature change. And then record the mass of the water, just the water, not the styrofoam cup. So you need to tare it when you put the styrofoam cup on before you add water. And also record the mass of magnesium sulfate. Those are all the information that we'll need, and we'll do this 3 times. The other thing that we're going to do in this lab is submit our results. Everybody in the lab is going to submit our results to a Google form such that we have everybody's data collected in a single Excel spreadsheet. And everybody's going to analyze the same set of many data. So if you did this 3 times, Imagine how many students there are. That's how many data times 3 we're going to get to analyze. Here is just a table for putting the result from the qualitative part, which is the first part that we talked about up here for these salts. And then for the quantitative part, we have some equations to solve. Now, I'm just going to go over number 2 again using some trial numbers that we use. You'll use one of your trials to do this. But let's assume that in one of your trials, you measured, I don't know, let's say 90.64 grams of water. You measured, let's say 66 grams of solvent, magnesium sulfate. I think magnesium sulfate is our solvent. Yep, magnesium sulfate. And our initial temperature, so let's use the same color. Initial temperature, not final temperature. There we go. Initial temperature was, I don't know, let's say 21.3 degrees Celsius, and the final temperature was, let's say, I don't know, 28.0 degrees Celsius. Let's use these as the starting point for our calculations. So the first part says to calculate the energy transferred to the solution, the heat energy. So we know that heat is the mass times the specific heat capacity times the temperature change. So let's calculate the mass of the solution and the temperature change. So the mass of the solution, would be the mass of the solute, which is 5.66 grams, plus the mass of the solvent, which is the water, which is 90.64 grams. This will come out to 96.30 grams. Okay. The other thing that we need to calculate for this is the delta T. So let's do that. The delta T will be the final temperature, 28.0 degrees Celsius, minus the initial temperature, 21.3 degrees Celsius. And so the delta T is 6.7 degrees Celsius. So if I plug this all in, the heat from the solution should be equal to the mass, which we got 96.30 grams. The specific heat capacity we know is 4.184 joules per gram per degree Celsius. And the delta T we know we just calculated as 6.7 degrees Celsius. If I plug all of these into my calculator, I should get 2,700 joules. This is my sample calculation. And so the heat energy transfer from the system, our system is the reaction, Rxn, is going to be negative 2,700 joules, right? This reaction is exothermic because the temperature increased of the solution. All right, now we need to calculate the moles of magnesium sulfate that were dissolved in the trial of this experiment. We know the mass of magnesium sulfate, so the moles of magnesium sulfate would just be the mass of magnesium sulfate, 5.66 grams, divided by the molar mass of magnesium sulfate. The molar mass of magnesium sulfate is 120.37 grams per mole, and nope, that was not what I wanted to cross out. That was what I wanted to cross out. And so this should give us 0.0470 moles, the 3 sig figs. Now, in the final calculation, we want to calculate the energy of dissolution per mole of magnesium. So the heat we get was negative 2,700 joules, but we want it per mole. So the delta H is going to be minus 2,700 joules divided by 0.0470. I get negative 57446 joules per mole. Sometimes, because this number is so large, we can write it as negative 57 kilojoules per mole. All right, so that's kind of the sample calculation that you need to do. The next part of this lab is to analyze the data from the entire class. So you need to do all of these calculations all over again for every single person's trial. Good luck. No, we're not going to leave you there. Because we're going to use Excel to make this very easy. And so this is the important part if you're not very comfortable using formulas in Excel. Now, after you submit your data to the class, after everybody's done this experiment, we're going to give you an Excel spreadsheet that kind of looks like this. That has everybody's data, their mass of water, their mass of magnesium sulfate, their initial temperature, their final temperature, the raw data that we collect in the experiment. Now, so this is all of our data. Now let's do the same set of calculation that we just did for every single trial. We don't need to do the calculations by hand. All we need to do is look at our calculations that we have. The first thing that we needed was to calculate the heat transferred to the solution. To do that, we first had to get the total, the total mass of the solution. So let's calculate that. The total mass of solution, and this is going to be in grams, and that is just, to get that, we go to the formula. So this is the first line with our trial. I'll press equal. I will scroll all over here to the left by pressing the left arrow key until it says A2. That's where the mass in grams of water is, right? And I'll press plus to add that. I'll scroll to the left again with the left arrow key, and this is the mass of the solute, the magnesium sulfate. So notice that the formula pops up here in the cell that we're working with, but also up here in this line is equal to A2 plus B2. That's what we want to add. We want to add the mass of the water and the mass of the magnesium sulfate. That will give us the total mass of the solution. So I press enter, and look at that. It added it for me. All right. So if I wanted to now copy this to every single cell, I can just click in this, go to the bottom left until it the plus sign changes to the solid plus line, and just drag down. The other way, I'm going to undo that. The other way I can do this is just copy and then hold shift, not hold shift, copy, scroll all the way to the bottom. I'm not clicking anything. Hold shift, then click, and then press Control V to paste it. And now it's pasted that in every single cell. So now we have the total mass of the solution. I just pressed escape to cancel the little moving lines. So now I have the mass in every single, for the mass of solution for every single trial. I didn't have to even think about it. Okay, the next calculation that we did was we find the delta T, the change in temperature. So let's do that too. So let's write change in temperature. And this is going to be in degrees Celsius, right? This is going to be the final temperature minus the initial temperature. So we'll do is equal to, scroll to where the final temperature is. It's in this cell. Press the minus sign. Press left until we scroll to where the initial temperature is. So it'll all be final minus initial temperature, and I'll press enter. If you want to do it the drag way, I'll go here. Look at my cursor. It's now different from when it's like not in the lower left corner. So click there, and then I'll drag this all the way down there. And there we go. That is our change in temperature. I'm just going to press Control S. Always save every 5 seconds. That's how I do it. All right, so this is our change in temperature. The next step that we did here was we used the mass of the solution, the change in temperature, to calculate the heat transferred to the solution using this equation. So let's do that as our next step. So I'll go over here. I'll put heat transferred to solution. And we know that this is in joules, so I'll put a little joule there. And so we know that this is going to be the mass times the specific heat capacity, which is 4.184, times the temperature change. So I'll put is equal to the mass. I'll scroll where we calculated the mass, times, right, that's an asterisk. So press not press anything, but type in the number 4.184 because that's the specific heat capacity. Again, multiplied by, and I'll scroll left with the left arrow to change in temperature. That's our delta T. I'll press enter. And that's our heat. 2699, which is rounded up to 2700 on my page, so that's correct. I use this first trial for these sample calculations. So that's one way to make sure that your numbers are correct when you do the formula. All right, so that looks good. Again, I would want to copy this to every single cell. Okay. The next thing that we did was figure out the heat from the reaction. So we'll do heat from reaction. Again, this was also in joules. And this is just negative, the heat from the solution to the solution. So I'll just do is equal to. I'll go to the cell right next door, press left. And then to make it negative, I'll just multiply it by -1. Press enter, and I'll get negative that value. So I'll copy this all the way down again. See, I'm doing the same calculations for all of these, 60 different trials instantaneously. I don't have to plug numbers in my calculator or any of that stuff. By the way, if all of these numbers bother you, I will just highlight them all like this, and I'll just reduce the number of decimal places because we don't really have that many sig figs anyway. We don't need that many sig figs. All right, so that's the heat from the reaction. The next thing that I did was calculate the moles of magnesium. I took the mass and I divided by the molar mass. So let's do that. Moles of magnesium sulfate, and this is in moles. And this will be equal to the mass. So I scroll to the left with the arrow key until I get to the mass of magnesium sulfate. I press the divide symbol, right? I can't see my formula anymore in the cell, but I can look at it here in this bar. So I get is equal to B2 with a divide symbol, and then I'll type in now the molar mass of magnesium sulfate, which is 120.37 grams per mole. I hit enter, and it takes me back to right here, the moles of magnesium sulfate. I'll just copy this down now for every single cell. I don't like this, so I'll select the whole thing. I'll reduce the number of sig figs, decimal places, because we have too many. All right, so that's our mole of magnesium sulfate. Make that a little bit smaller, like that. Let's make some of these smaller, why not? There we go. All right, next thing that we calculated was D, which was the enthalpy per mole. Well, this step we don't have to calculate for each individual trial. We're going to do this graphically. So here we divided by the, let's look at it. We took the heat from the solution, sorry, the heat from the reaction, and we divided by number of moles. So if we wanted this to be a slope of a graph, then number of moles should be in the x-axis, and the heat from the solute reaction should be in the y-axis, right? Heat from reaction, and this will be number of moles. And if we were to plot a graph, let's use orange, the slope here will be heat rise over number of moles. So if we plot every single data and then we get the slope of that graph, what we're effectively calculating is just the heat from the reaction for every single trial, sort of averaged over every single trial. So let's do that. So on the x-axis, we should have number of moles. On the y-axis, we should have heat from reaction. So remember, when we plot, the first column becomes the x-axis and the second column becomes the y-axis. So what I want to do is switch these around. So I'll just grab there, and actually I'll just copy this over here. I'll have to redo the formula, right? So the heat from the reaction is just this G cell, heat from the solution, but negative. So I'll be is equal to heat but times -1. I'm only copying it over because I forgot how to move the cells over without losing the formula. And so I'll drag this down all the way. So now it's set up nicely for me to do a graph without having to think about switching the x and y axis. So we have moles on the x-axis, heat of the reaction from the y-axis. So I'm going to click these two. So I click here, hold shift, click here. So I select both columns. All right, now I'm going to scroll all the way to the bottom, hold shift, and click on this cell here, and I'll select everything. So if you let go of shift and you scroll up, you'll notice that I've selected everything. I'll go to insert, click here for charts. I want to make sure I insert scatter XY or bubble chart, and do that. And there is all of my data. I'll go here, quick layout. I'll choose this option so that I have the titles and things that I can fill in. Let me just click on this so we can see more of what we're working with. So let's say there's a lot of data points like this here that are clearly errors, or they have large errors associated with them. We can click on them to try to remove them from our data point. So in this example, I just click on this dot. Let's say it's this one. So let's just click off, click on again. I don't know, there's this one all the way out here. Let's say that's one we want to remove. I'll click it a few times so that only that dot is highlighted. I hover over it, and I see that the x value is 0.0618 and the y value is negative 615. So I'll then scroll here to find that y value of negative 615. It's right there. Something went wrong here. Not sure what it is, but I'll highlight both of that and I'll delete it. And so if I go back to my graph, we see that that data point is removed. And you'll do the same thing for all the points that you think should be removed, so that because there are errors in the calculation, or errors in the experiment rather. And that will help to improve your y-squared value. Right now you can see for this data it is horrible. You'll remove as many points as you need to, because they're clearly outliers. All right, so hopefully that all makes sense. You can rewind this video to see how I did any of the calculations again. But by the end of this, you should be experts at using Excel. I'll drag this over so we can see all the data points that we did. All right, so that will bring me to the end of my video. Your post lab will be due, the day after classes. So make sure you get all of this done. But this is one quick way that we can use Excel to quickly run calculations for lots and lots of data points that would take us ages to do by calculator. All right, that'll bring me to the end of this video. Hope we learned something, and I will, or your instructor will see you in lab. Bye.